But now there's various ways to do it, and some of them are, I mean, they're all actually, a lot of them are valid. They give you different answers. You have to decide what it is that you prefer. So for example, you could measure the distance to the line, by projecting perpendicularly. Or you could measure instead the difference between, for a given value of x, the difference between the experimental value of y and the predicted one. And that's often more relevant because, these guys are actually maybe expressed in different units. They're not the same type of quantity. So you can't actually combine them arbitrarily. But anyway, so the convention is usually we measure distance in this way. Next, you could try to minimize the largest distance. Say we look at where's the largest error and we make that the smallest possible. The drawback of doing that is experimentally, very often you have one data point that's not good because maybe you fell asleep in front of the experiment and so you didn't measure the right thing. So you tend to want to not give too much importance to some data point that's far away from the others. So maybe instead you want to measure the average distance. Or maybe you want to actually give more weight to things that are further away, and then you don't want to do the distance, but the square of the distance. So there's various possible answers, but one of them gives us actually a particularly nice formula for A and B, and so that's why it's the universally used one. Okay, and so here it says least squares. So that's because we'll measure actually the sum of the squares of the errors. And why do we do that? Well, part of it is because actually it looks good. I mean, when you see these plots in scientific papers, they really look like the line is indeed the ideal line. And the second reason is because actually the minimization problem that we will get is particularly simple, well posed, and it's easy to solve. So we'll have a nice formula for the best A and the best B. So, if you have a method that's simple and gives you a good answer, then that's probably the good one. So, okay, so we have to define best. And here it's in the sense of minimizing the total square error. So, or maybe I should say total square deviation. Let me do that instead. Okay, so what do I mean by that? So the deviation for each data point is the difference between what you have measured and what you are predicting by your model. Okay, so that's the difference between yi and axi plus b. Okay. So now, what we'll do is we'll try to minimize the function capital D, which is just the sum for all the data points of the square of the deviation. Okay, so let me emphasize again, this is a function of A and B. I mean, of course, there's a lot of letters in here, but xi and yi, in real life, there will be numbers given to you. There will be the numbers that you have measured. You've measured all of this data. They are just going to be numbers. You put them in there, and you get a function of A and B. Okay? Any questions? No. Yes? No? Okay. So how do we minimize this function of A and B? Well, let's use our new knowledge. Let's actually look for a critical point. So we want to solve for partial D over partial A equals 0 and partial D over partial B equals 0. That's how we look for critical points. So let's take the derivative of this with respect to A. Well, so it's going to be, well, the derivative of a sum is sum of the derivatives. And now we have to take the derivative of this quantity squared. So, okay, remember how we take the derivative of a square. We take twice this quantity times the derivative of what we're squaring. So we'll get 2 times minus yi minus axi plus b times the derivative of this with respect to a. What's the derivative of this with respect to a? Negative xi, exactly. Okay? And so we'll want this to be 0. And partial d over partial b, we do the same thing, but differentiating with respect to b instead of respect to a. So again, sum of squares, twice yi minus axi plus b, times derivative of this with respect to b is I think, negative 1. Okay? So that's the equations we have to solve. Well, let's reorganize this a little bit. So the first equation so see there's A's and there's B's in these equations. I'm going to just look at the coefficients of A and B. If you have good eyes, you can see probably that these are actually linear equations in A and B, although there's a lot of clutter with all these x's and y's all over the place. Okay, so let's actually try to expand things and make that more apparent. So, first thing I will do is I will actually get rid of these factors of 2 that are just, not very important. I can simplify things by 2. And next, I'm going to look at the coefficient of A. Well, I will get basically A times xi squared. Well, let me just do it, and then it should be clear. So I claim when we simplify this, we get xi squared times A plus xi times B minus xiyi. And we set this equal to 0. Okay, do you agree that this is what we get when we expand that product?